We've now moved down onto the shore, and every time I come here, it's a surprise as to whether or not there's what the state of the beach is. Every single trip I've been on, there is a different size beach in this little area. Today we have some beach. Last time I was here, there was no beach sand at all, and that was last time I was here. It was low tide, so there should have been a beach. And the fact that we're almost at high tide and there's a beach means that at low tide there'll even be more beach, because the tide will go down, pushing the water out, and the beach will grow because of that. I was just talking about the wind, and I have a speculation. I don't know if it's true or not, but perhaps because of this onshore breeze, we are bringing in more sand in the waves, making the beach larger than in the winter when the sand blows out and we have a smaller beach. But there are other reasons we have beaches. The beaches change in here. Aside from the tide and the wind, we have waves, and you can see out there that we have waves, and they're not very big, but they are crashing close to shore. And one of the observations you can make here is, are the waves crashing straight onto the beach, parallel to the beach, or are they at an angle to the beach? And so the idea is, what you need to do is watch somewhere, find a rock on the jetty, and then trace a wave when it hits the jetty and see when it hits the beach. And if it hits the beach at the same time, you know it's parallel. But if it doesn't, you know it's not parallel. And so I pick where they're first breaking out there is about 20 yards away, and I'm watching that wave, and it doesn't hit the beach until much further in. So the waves are breaking at an angle to us here. And so because of that, with the waves doing that motion will set up what we call longshore current, and it will carry sand and water down the beach because of these waves not being directly head on. In general, along the coast here, we have a longshore current which is moving because of this angle where it's coming in like this. It is moving things from the east to the west. That's not to say that it's every day that way, but the majority of the days the longshore current is from the east to the west. So that sand we're seeing here is transported from somewhere to the east. I know that they did a beach nourishment. They increased the sand at the beaches in Galveston over the last 2 winters. So perhaps we have a beach here because of this longshore current bringing sand from Galveston down to here. So this little town we're in, Surfside, doesn't have to do beach nourishment. They just have to wait for Galveston to do it, and then the sand comes down here and they get their beach. So there are 3 different factors here that control whether or not we have this little beach I'm standing on. There's the wind, the waves, and then the tides and the current. Another feature we have at the beach is obviously the sand. So we looked at the sand at the last stop at the Brazos River. And so if we pick up the sand, you can look down just even at the surface here, and you can see that we have a little white coating that is different from the brown underneath. And if we pick it up, we can look at it and see how it compares to the material at the Brazos River. And if I look at this carefully, and I gave everybody hand lenses at the first stop to do this, you can look at the sand here. And what do you see? Well, it's very different from the sand at the Brazos. It does not have the same ingredients. the grain size is also very different. So you can look at it and you can see black specks, you can see white fragments, and the white fragments are all broken up pieces of shell. And this area here, you can see the shells on the beach. A lot of people like to come to the beach and collect seashells. And even if you look down the beach from where I'm standing has lots of shells. You look down the beach and you see that there are no shells. And so this little corner here that I'm standing in the jetties, the waves and the action brings in coarser sediment here than down the beach. And so if you want to collect shells, this is a great place. And there are lots of shells. You can see they're broken up. Okay. I need to collect one of these guys. And I just collected a few pieces of shells. Most of them are, as I say, are breaking up. They're going to break down and become pieces of the sand. And you will notice that I have two colors of shells here. One is very dark and the others are light. And the light ones are fairly new. And these dark ones are, or this is what I have been told by geologists who work down here, that these dark ones come from the last ice age. And so that these are really old shells. I don't know exactly how old, but a shell is made out of a carbonate. If you remember that term from physical, we have two different carbonates. We have calcite and aragonite. And most shells are made out of the form aragonite. And when they age, it turns into calcite, because that's the stable form on the Earth's surface. And when it transforms, it kicks out organic material and turns the shells black with age. And so this black is saying that this shell has had long enough to transform and is pretty old. And some of them, as I say, could be tens of thousands, hundreds of thousands of years old. I don't know. People who study them will take these and try and get carbon dates on them, get back in the lab. But so if you see the black shell, it's not a different kind of shell, it's just an old shell. And so if you want, go ahead and collect old and new shells. When I was talking, I realized that many of you probably have not heard this term aragonite, but you might have heard the term polymorph. And a polymorph is a mineral with the same composition but a different structure. The example in your textbook is graphite and diamond. And they look incredibly different, but they're the same thing. They're both carbon, but they have different structures. And the same is true with calcite and aragonite. They both have the same chemistry. They're both calcium and a carbonate ion, CO3, but they have different structures. And so it's when they change from one structure to another that they become, their structure changes. Typically, aragonite is stable at high pressures in the earth, and so it is normally found in subduction zones, high pressure areas. And calcite is the form that's stable on the surface of the earth. Why animals make aragonite? Ask a biologist. I don't know, but they do. I just know that as a fact that they make aragonite in their shells. Maybe it's because it is a stabler form. If it's a high pressure form, it's probably going to be more robust and make a better shell. On this trip, I know geology is generally the study, you think of the study of rocks. And we talk a lot about rocks, and you don't see many rocks on this trip because we're dealing with coastal processes. However, the Army Corps of Engineers has kindly provided us with two different kinds of rocks at this stop. And do you remember what the major classes of rocks are? We have And usually people can't give it to me, but we have igneous, metamorphic, and sedimentary. And we have two of them here. Okay, what are they? Which are they? We obviously have the red rocks. Everybody generally can identify these red rocks. And then we have these more nondescript gray rocks here that, and I should point out, all of these rocks are Texan rocks. They would not quarry rocks from far and bring them. So, and I know that most of you don't get taught much about the history of Texas geology, but about 1 billion years ago, this Texas was a subduction zone with an island arc. And in island arcs, you are taught usually it's volcanoes, but what crystallizes at depths are granites. And so all behind me here are the granites that crystallized in an old subduction zone 1 billion years ago. So those of you who are standing up there or seeing those rocks, you're standing on rocks that formed 1 billion years ago. Very impressive. After that time, when there was this tectonics, Texas became a passive margin with not much happening. It just then records sedimentary history from pretty much most of Texas was then influenced by some areas like what we're seeing right now, the coastal processes. And in the Cretaceous time period, the time of the dinosaurs, most of Texas was underwater, under the ocean. And in the ocean, as you can see, we have sediments, we have sands, but we also have the water. And in the water, what gets deposited are limestones. Deeper in the water, not influenced by the tides, by the forces that are here, where you don't have the sediments being carried offshore, we get reefs. Offshore Texas, there are reefs right now. Great places to go diving, great places to go fishing. But so in the Cretaceous, we had lots of limestones being deposited through most of Texas. And so this sediments here are old limestones. And I can prove that to you. You might have seen this test when you were, if you took the lab or it's in the textbook. One way to identify calcite and limestone is they fizz. So I have a little bottle here which has a very weak acid. It's similar to vinegar. You could bring vinegar to the beach and do this if you wanted to. But what you do is you come to a rock and you drop on the limestone, the acid, and it will fizz because the acid is breaking these bonds in the calcite between calcium and the carbonate. And when it breaks that bond, the carbonate is CO2 gas. And so the gas bubbles away, and it makes it a very easy way to find whether it's limestone or not. And so if you want to test it, go ahead. Notice these rocks right here, what you think are rocks. They look like conglomerates, like they would have formed in a river with pebbles, rounded pebbles with a matrix. And it's hard for you to tell, but this is not a rock. This is a piece of man-made concrete. And I can tell that because I can do the test. And you can see that the matrix around the pebbles is fizzing. And so the matrix is limestone. And in a river, you don't have limestone, you just have mud. And so I know this is the binder, and most concrete is calcite. And so they take lime, which is just calcium oxide, they mix in water and CO2, and it makes calcite again. And so this is a man-made rock. It is not a natural conglomerate. Another feature you might notice about these blocks is, and many of you don't think of these as sedimentary rocks because we're taught that sedimentary rocks are layered. they have beds, and you see bedding, and most of the pictures in your textbook show bedding. And you look at these, and they're just large chunks of gray rock without obvious bedding, and that's because of the way these rocks formed out in the ocean. There's always continuous deposition from the ocean. It's very rare to get beds, very distinct beds in the ocean, because there's no reason for the deposition to stop in the middle of the ocean. So they're just large, massive limestones. The other thing you can notice, you can look at the granites and notice that they're angular. They still have drill holes, and they're make a nice barrier up there. Where the limestones down here, these are also quarried rocks, and if you look at them, they're all very rounded. They're not angular anymore, and this shows that we have different rates of weathering, that the weathering is not really affecting the granites, but the limestones down here are very weathered and turning into angular rocks. Some of them are actually very small, and so that on the coast here, you can see then the effects of differential weathering rates. Because we don't have differences in climate, we have the same climate up on there and down here. It's just that we have much faster chemical weathering down here than we have mechanical weathering at the beach. Okay, we're now going to look at the granites a little bit. If you remember, granites are composed of they're felsic rocks, meaning they have a lot of feldspars in them. That's what the fel is, and the sic means they have a lot of silica, quartz. And so if we look at a rock, it has lots of feldspar, which in this case is large crystals of potassium feldspar. And there's also grayish quartz, and then there's a white feldspar, which is the other kind of feldspar, which is the plagioclase feldspar. And so we have large potassium feldspar, plagioclase feldspar, and quartz. Those are the three main ingredients in a granite, and then there are sometimes mafic minerals. And in this case, you can see right here, there's a fairly large chunk. This is a large chunk of biotite mica. These are all black biotite micas. It could have amphibole, it could have muscovite, but in this rock here, it's biotite, and you can see that if I go like that, if I had a knife, you could flake it off. The other thing you can see is if you move your head around and move it in the sun, that we know these are potassium feldspar because they have cleavage. Remember, cleavage is the term of when a mineral will break. And so if you move your head around, you can then see, now the sun just disappeared. But from my angle, the sun is coming down and I see a flat surface there, a flat surface there. And if I stand the right position, get my eye right, I can see flashes of sunlight on the cleavage. And that's how I know that that's definitely a feldspar and not something like quartz. And if you move your head around on these grayish crystals, you'll never see cleavage because quartz doesn't have cleavage. Now most of you, when you think about a granite, you think of granite countertops. And most granite countertops, the features are all the same. There's crystals and they're just in a homogeneous pattern. It means they all look the same. If you look at most of these blocks, you'll see that they all are very similar looking. But there are processes going on during cooling of a magma chamber that you can see here. This is not something you get taught in a lecture, but I'm going to show it to you because one of the things that's important to geologists is making observations. And we can make observations at many different scales here. And you can see in this particular block I'm standing in, there looks like a band going through it. And there are big crystals that grow into it. So this was probably open space. It was probably as it was cooling, and it was almost all crystalline. It was strong enough that it cracked open and had open space. And so then these crystals grew into the open space, kind of like if you've seen a geode. Geodes are the same thing, where crystals are growing into open space. So these things grew into open space, and then as it was cooling further, a bit of magma came into here, and because this was pretty much solid and crystallized, it cooled very quickly, because it just was at a much different temperature between here and here. And so as it cooled quickly, it made very small crystals. And so we have a small history here, where the rock is telling us a story about something that happened as it cooled, that it got strong enough to fracture and have open space, have crystals still growing, but then something happened and another magma came in and it cooled very quickly, and you can't really even see the crystals in this part. Here we have a block of granite, and if you look at it carefully, you can see that again we have potassium feldspar, plagioclase feldspar, and quartz, and the biotite mica. And this block, if you move your head around, this one is great for the cleavages. And you can see the large potassium feldspars with big cleavage. And so one of the things to look at is we have these big potassium feldspars. What's the size of the plagioclase, and how do they occur? Well, there's the plagioclase. I move my head, I can get small fragments, but the plagioclase is all small, and the potassium feldspar, these pink ones, are big, they're square, they're nice crystals. And so I can look at this and make a hypothesis that the first crystal to form in here was the potassium feldspar as the magma was cooling. But if I look carefully at crystals, like this one right here, in the center of some of these crystals, of potassium feldspar, there are other minerals. In this case, there's quartz and biotite. So it's a dynamic system. Here, a little bit of quartz and biotite formed, and then the potassium feldspar started to grow and grew over it. And so, and the same thing can be seen up here. Here we have a large crystal of plagioclase feldspar with a little bit of biotite in the center. So biotite started to crystallize, then the plagioclase, and then it was surrounded by small scale potassium feldspar. And so if a geologist comes here and looks carefully at these crystals, they can get a history. You're taught about Bowen's reaction series and cooling of a magma, and you're taught that it's a very orderly sequence from mafic to felsic crystallization. But if that was the case, we'd get the mafic and then felsic, but then why would we have changes in this order of crystallization? Like here we have a pink potassium, a plagioclase, more pink, and this is showing us that cooling in these magmas is not as slow and steady as you might get from a textbook. And the other thing you might notice here is here we have a zone where it's mostly pink crystals and white crystals and very little biotite. So something happened. So these magma chambers are much more dynamic than the orderly crystallization sequence you get from your textbook.